So since this is our 25th anniversary, this gives us a chance to reflect back on our past achievements. So I've prepared a slideshow of our favorite moments of previous shows and synced it to Brahms' Lullaby. I'm sure you're going to enjoy it.
Wait, Peter, no, stop that. They don't want to see a slideshow. They came to have fun.
Rachel, what are you doing up here? You're supposed to be backstage working.
Well, I knew that you wanted to celebrate the 25th anniversary.
Yes.
So I built something special.
An outhouse?
Oh, it's not an outhouse. It's a Type 40TT TARDIS. You know, a time machine.
Ah, a time machine. Well, you know, we could set the time machine to 1984 to the very first Wonders of Physics show.
Exactly, and we can yoink out the original Professor Sprott and bring him back here to do the show today.
Yeah.
So what do you guys think? Do you want to use the time machine, or do you want to see the slideshow?
All right, time machine. All right, but show me, how does this thing work?
Sure, all you have to do is you turn this knob here, and then you push that button.
Okay.
You operate it, and we'll do a countdown. All right, ready? 5, 4, 3, 2, 1.
Well, I'd like to thank you for coming to the 25th anniversary of the Wonders of Physics. We hope you'll all come back next year for our 26th anniversary.
Oh, wait a minute. What do you mean come back? Well, you know, we must have gone forward 60 minutes instead of backwards. Rachel, this thing's not working. Get back here. Well, so Rachel built this time machine off of plans on the internet, and we tried to go back to 1984 to bring you back for the very first show, but, you know, before we start today, you need a proper introduction, so quick, behind the curtain over here. Right there, and just cover up real quick. There you go. All right, ladies and gentlemen, may I present to you the king of the clocks, the master of the metronome, the wizard of the watch, and that traveler in time, Professor Clint Sprott.
Welcome to the Wonders of Physics. Now, I would like to take you back in time today to visit some of the demonstrations that we've had over the past 25 years in the Wonders of Physics. And I'd like to begin with some demonstrations of motion. A ball, if I drop it, it falls toward the Earth. And you know that happens because of the Earth's gravity. But what I would like to do is step up on the lecture bench with this ball in one hand, and in the other hand I have a ball of cotton. And I'm going to drop the two side by side. Who thinks the ball of cotton will hit the ground first? Who thinks the ball will hit the ground first? Who thinks they will hit the ground at exactly the same time? Well, you know, that's fine in physics to have different opinions, but we don't just vote. We do the experiment, so let's try it. You probably noticed that the ball did hit the ground a little bit before the cotton, but not for the reason that you might suspect. Not because the ball is heavier than the cotton, but because of the air resistance. The air affected the motion of the cotton more than it did the motion of the ball. Now, I can illustrate that by doing the same experiment inside this tube. Can you see what's in there? What?
It's fuzzy.
Fuzzy, that's right. It's a ball of cotton and a penny. That's right. Anything else in here? Air, that's right. So let's try this experiment once more inside this tube. You can see how slowly the cotton falls this time. The penny, of course, falls right away. Now, the reason we do it in this tube is so that we can remove the air. And for that purpose, we use this vacuum pump over here. So I'll connect the hose here. Mr. Wykes will turn on the vacuum pump, and you will see the pressure come down towards zero. Now, when it gets down to zero, we will have removed all the air from the tube. Well, it will take forever to get the last little bit of air out, but fortunately we don't need to do that. At this point I can close this valve, then we don't need the vacuum pump anymore. I can take this off, and now we have a tube with what in it? A penny, ball of cotton, anything else? There's a little bit of air in there. We call it a partial vacuum. Now let's see what happens when I invert it. You see how much faster the cotton falls. Now, to show you there's no tricks, I can let the air in and do it one last time. Okay? So that shows you that in the absence of air resistance, all objects fall at the same rate. It doesn't matter how heavy they are, it doesn't matter what color they are, it doesn't matter what they're made out of. None of that matters. Objects fall at the same rate if they're acted upon only by gravity. Now I want to show you another demonstration that involves motion. Here I have a little can. I'm just going to roll the can across the lecture bench to see if the bench is level. Well, I thought for sure we'd level the bench before the lecture, but let's try it the other way. Well, that's a little odd, isn't it? It looks like magic, but in fact it's not magic. It's a principle of physics. Inside this can is a spring and a weight, and when the can rolls, it winds up the spring. And this is an illustration of the conservation of energy. When the can starts, it has so-called kinetic energy, energy of motion. Then as it slows down, that kinetic energy is converted into potential energy of the wound-up spring, and then the spring unwinds, releasing the potential energy and causing the can to move again. So that's an illustration of one of the most important principles in all of physics, the conservation of energy. Now, I'll show you another demonstration. Do some of you have a yo-yo? You know those things that on the end of a string? You've seen those. Well, here is our very large yo-yo. Except I'm not going to use it as a yo-yo. I'm going to set it on the lecture bench, and I'm going to pull on the string. And I want to ask you a question. When I pull on the string, do you think the spool will roll toward me or away? Who thinks toward?
Toward.
Okay, who thinks away? So most of you think the spool will roll away from me when I pull the string. Let's try it. You were wrong, weren't you? But let's see. In fact, I can make it move toward me, or I can make it move away from me. Can you see what I'm doing differently in the two cases? What? I'm moving my hand, aren't I? When I want it to come toward me, I hold my hand down low like this, so there's a small angle here, and it comes toward me. When I want it to go away, I hold it up like that, and it makes a large angle. Now that suggests that there must be an angle in between somewhere where it doesn't roll toward me, and it doesn't roll away from me. Let's see if we can find that angle and see what happens. Right about there, if I pull, it just slides across the table without rolling either direction. And of course, this is one of the principles of physics that goes back 300 years to the time of Isaac Newton, who was a famous physicist who gave us the laws of motion. Now, I want to show you another example here of something that moves. Here I have a chain, metal chain. If it were a little bit larger, I would be able to put it over the top of my head and I could wear it like a necklace. Well, I don't want to do that, but I do want to put it on this wooden spool back here that's connected to an electric motor. And I'm going to turn on the motor and let the chain begin to rotate very rapidly. At first it slips, but then due to the friction, it stops slipping. And then I'm going to take a stick and I'm going to nudge the chain off the wooden spool, and we'll see what happens.
Professor Sprott, I've got this sonic screwdriver I think can help fix the time machine.
Okay, let's try it. Okay.
I think it'll work now. You keep that just in case.
Okay. Well, Professor Sprott, you know, I really would like to try the time machine one more time.
Well, okay, let's see if it works. Excuse me, who are you?
Newton! Isaac Newton! Sir Isaac Newton! From England!
I see that. Are you injured?
Yes. I was just coming on the street and this fell on my head. Where am I?
Well, you're at the University of Wisconsin, and this is the wonders of physics.
Physics? I know all of physics. I know all of physics. And what do you think? What's this? What?
Well, these are some of our demonstrations. Would you like to see one of these demonstrations?
Yes, yes, yes. The apple. That's an apple.
No, that's no apple, but it is a very heavy steel ball. It weighs about 5 pounds. And it's suspended from above by a string. And down below there are 2 identical strings. Now what I'm going to do is pull down on this string, and I'm going to pull hard enough that one of the strings will break. Who thinks this string will break when I pull? Who thinks this string will break?
I know everything. I'm Newton. This string will break.
Well, let's try it. We don't just argue in physics, we do the experiment.
Oh.
So, Sir Isaac Newton was wrong about that. But you know, in physics, we don't like to draw a conclusion based on a single observation. We always like to repeat our experiments. So let's do it again with the second string and see what happens.
Brilliant, brilliant.
That time, the upper string broke. Could you see what I did differently in the two cases? One case, I gave it a quick jerk. In the other case, I pulled very slowly. And it was the inertia of the ball that made that happen.
Inertia! That's what I've been looking for. Inertia. And gravity. I must get back. I must write a book. Inertia and gravity. Inertia and gravity. A little momentum. Plant it and make a tree. Inertia. Inertia and gravity. Inertia and gravity. What was your name?
I'm Professor Sprott.
I will dedicate my book to you, sir. Inertia and gravity. Inertia and What was your name?
Sprott. Please spell it right.
With 2 T's. Thank you. Inertia and gravity. Must get back. Inertia and gravity.
Well, I'm not really sure about this time machine stuff. That looked an awful lot like Professor George Rollins from the University of Warwick, and he's been with us in the past helping out with these shows. So it may be someone's playing a trick on me, but anyway, where were we?
Professor Sprott, I don't think that sonic screwdriver works. So, I need to get a repairman out here. So I'm just going to give him a call.
Well, okay, but please hurry along.
You called?
My goodness, it's David Willey, the mad scientist from The Tonight Show with Jay Leno.
And you're Professor Sprott, yeah?
What are you doing here?
Oh,
I'm the
thought you were the
repairman.
repairman.
Yeah, Leno doesn't really pay that well. I have to moonlight. So what appears to be your problem?
Well, Rachel built this time machine from your plans off the internet.
Okay.
And we were trying to bring Professor Sprott from 1984, but it doesn't seem to be working very well.
Oh, maybe I can fix it for you and... Ooh, you got some of my favorite toys here. I do shows like this. I tell you what, I'll fix your time machine if you let me play with some of your toys for a while.
Sure.
That okay with you?
Yeah.
Yeah? That okay with you folks? Yeah? Okay. Boy, I got some nice stuff here for me. Oh, balloons, I like these. These are great. What I've got here, if I think, liquid nitrogen. This stuff looks like water, but it's not. It's 200 degrees below the freezing point of water. This is air. And look what happens to things if you get them cold. They shrink. I just wanted to show you that as a quick intro. If you blow on that for me and it'll blow right back up again. Because I use this stuff in my shows a lot. I started doing physics shows after being inspired by this gent here. And sometimes when I do shows, I'll use this liquid nitrogen, and afterwards, somebody will come up and say to me, "That's really cool stuff." And I tell them, "No, actually, it's very, very cold. It's not just cool." They say, "No, I don't mean that. I mean, it's really neat. I want to take some to school for show and tell. Where do you buy it, and can I get some?" They say, "Well, I tell them where to buy it, and yeah, you can get some. But to get some, you got to have a special doer to put it in." They say, "No, I haven't got a special doer, but there again, how much can they cost? I'll buy one." I tell them, "Well, this little doer here, just this little one was probably $200. So, "Oh, no, I can't do that. That's way too expensive. I'll just go down to where you get this gas, and I'll have them put some in a Pepsi bottle for me." And I have to tell them that only an idiot would put liquid nitrogen in a Pepsi bottle. No, it's okay. This is a Mountain Dew bottle. Okay. Actually, of course, that's not the silly bit, is it? What's the really silly bit? Putting the top on. Especially if you put it on really hard. See, because what's going to happen is when the liquid in this bottle tries to turn back into a gas, the molecules are going to get to be 10 times further apart. Now that's 10 times this way, 10 times this way, 10 times this way, 1,000 times the volume. I put about a cup of liquid nitrogen in there. It's going to turn into 1,000 cups of gas. I don't think 1,000 cups of gas are going to fit in that Pepsi bottle, a Mountain Dew bottle. So we'll come back in a minute and we'll see why it is you should never, ever put liquid nitrogen in a sealed container. Now, while we wait for that, I need a young lady to help me with a demo. Oh, hand shot up immediately. Gotta love enthusiasm. Hi, what's your name? Hi, Aaron, I'm David. I am very pleased to meet you. If you're okay with this, we are gonna have a race. We're gonna see who can empty a bottle of water the fastest. This is water, it's just got food coloring in. Which would you like? You want the green one? Okay. On the count of 3, start drinking. 1, 2, 3. You're not going to do it, are you? You are a very sensible young woman for not doing it. Tell you what we'll do is this. We'll just have a race here. We'll see who can empty their bottle the fastest, but just by emptying them into here, okay? But I'm going to win. There is a really good scientific principle as to why I am going to win. I'm going to cheat. Yeah. All you're allowed to do is take your bottle, turn it upside down, hold it upside down very, very still. Can you do that for me? You promise? You can start. Go on. I'll give you the lead. She turns it upside down. I do mine, but I cheat. I put a swirl on mine. Even though she started first, every time, I finish first. I think you at least deserve these people to give you a nice big hand. Thank you very much for helping. Now, question is, of course, why did I know I was going to win? I said I cheated, but really there is a good scientific principle as to why I won. See, what was happening with your bottle was that air was trying to get up into the bottle. That's light stuff trying to get up. Heavy stuff, water, was trying to get down out of the bottle. They got in each other's way. And they made the water in the neck of the bottle gurgle. What I did was I put a spin on my bottle, and that made the heavy stuff move toward the outside. That let the light stuff move up the inside. Now, I see you're wondering why I've got charcoal lighter fluid in my hands. I'm going to put some on this piece of paper here and set fire to it. Because it turns out that a flame does very much the same as the air in your bottle did. You see, there's light stuff trying to get up, that's the flame. There's heavy stuff trying to get down, that's the cold air. They're getting in each other's way. We don't say a flame gurgles, we say what? It flickers. But you can see it's not a very high flame. But what did we do with my bottle? We put a spin on it. That made the heavy stuff go to the outside, and the light stuff was able to get up the inside. Let's see if we can get the light stuff up the inside this time. And sure enough, we can. We get ourselves a wonderful little tornado of fire. Now, wait on a minute. For the knowledgeable, Southern Hemisphere. And of course, it works just as well. Yeah! Yes, yes, yes! That is why you should never put liquid nitrogen in a sealed container. Now, I'm guessing, yeah, I should probably put that flame out before it gets to the smoke detectors. Notice I didn't try and blow it out. Couldn't have done that. I put a cover on it. See, for something to burn, it needs 3 things. You need fuel, you need heat. What else do you need? Some people said air, some people said oxygen. You're both right, because of course it's the oxygen in the air that things need to burn. Oxygen's basically about the other 20% of the air after the 80% of the nitrogen. There's a few other things, but not that many. Now, let me show you something else where we need air to burn. A friend of mine worked last summer for NASA, and he said, came to my house one day, he said, David, I got this great demo I want to show you. It's how they demonstrate rocket engines at the space camp. So you need a 5-gallon bottle to act as the rocket engine. Well, we got one of those. So you need some ethyl alcohol to act as the fuel. Got that. You need a source of ignition. So, first thing you got to do is you got to mix the fuel with the air. Fuel doesn't burn unless it's mixed with air. So, let me pop this on here, and I'll be the equivalent of what? Not in a rocket, but in your car, a carburetor, or a fuel injection system, right? Basically, I'm mixing the fuel with the air. Now, I can't send the rocket upwards because I'm not sure where it's going to land. And sending it sideways isn't such a great idea either. So I'm going to have this go as though I was trying to get downwards. But we'll still see a rocket effect, I hope. Maybe we could just dim the lights a little. Let's see if this works as a rocket. Sure enough, it does. Now, they call that a whoosh bottle. Now, we had a young lady help me a little while ago. I think it's only fair if we have a young man help me with another demo. I need a volunteer. You're going to volunteer? Come on up here. What's your name? Hi, Jamie. I'm Dave. Pleased to meet you. You ever play with bubbles? Blow little soap bubbles? Yeah? Kids don't do this. When I was a hippie, honest, I was once, we used to play with soap bubbles a lot. I got to the stage where I wanted to blow really big bubbles. I figured out how to do it. I'm going to make a bubble big enough that we can put you inside it, okay? Come on over here. You step right up on here. Let me hold it still. No, on there. Go on. That's it. Up on top. Turn and face this lovely audience. There we are. Yep, keep your hands in your pockets. Let's see if we can put him inside a bubble. And sure enough, yes we can. We can put you inside a really big bubble. Now, if Mom's out in the audience, don't worry. This is just soap detergent, right? Dish detergent. Now, grab my hand, because it's going to be slippy when you run down. Come on, don't slip. Great. Give this man a big hand. Thank you. Oh. I love doing this stuff. Oh, we've got a classic here. You remember when we poured the liquid nitrogen on the balloon, how it shrunk? When things get cold, they shrink. Well, when things get hot, they expand. I'm going to expand the air in this bottle in a minute. And I'm going to do it to do a classic demo for you. Getting air pressure to push an egg into a bottle. Now, you see, this egg doesn't in any way fit in this bottle right now. But if I take a piece of paper, let's take this piece of paper, set it on fire. If I put this in the bottle, it'll make the air in the bottle expand. And then, whoops, come on, get in there. If I put the egg on top, yep, sure enough, it pops right into the bottle. Now, as I said, I do demos like this in my own shows. And sometimes, after shows, people will come up and talk to me. And one time, this one lady comes up to me and she said, David, that was a good show, thank you. And thank you very much. She says, but I wanted to ask you something. Why do you do this? Is it the big money that they pay you as a teacher? Well, we must have some teachers in the audience because you're laughing. You know that it's not the big money they pay you that makes me do this. And this look comes over this lady's face and she says to me, it's not the money. It's, you do it for the children. Oh, no. I do it for the toys. That's what I do it for. These people here have made me one of my favorite toys. Bed of nails. Feel the nails, ladies. Are they sharp? Yeah, they're sharp. All right. That's not the best bed of nails they made me. This is the best bed of nails they made me. This is big enough to lie on. Yeah. Now, on the subject of lying on beds of nails, a serious piece of advice to you. Never ever lie on a bed of nail. Yeah, think about that for a minute. Never ever lie on a bed of nail. Always lots and lots of nails. In a minute, we'll get a volunteer and we'll get them to lie on this bed of nails for us. Now, I want to show you first, though, before we even do that, that these nails really are sharp. Hey, cabbage here, imagine it's some part of my anatomy. Well, not the head, actually. Let's see if the nails are sharp. Oh, yeah. In fact, probably sharp enough that, yeah, I can even pick that up. Now, if I pull quick, but think, you would not want that happening to your shirt or blouse if you were inside it, right? So, yeah. But we are going to lie a volunteer on this bed of nails. We have to take some precautions, because the demo I'm going to do is to show you why it is you want the front of your car to crumple up if you're in a head-on accident. Back in the 40s, 50s, they used to think that if they made the cars really strong, then they wouldn't hardly even dent in an accident, and that would keep them safe. And it did. The cars didn't keep the people inside safe. So these days, what we do is we build cars so that if you're in an accident, the front of your car will crumple up. And that crumpling up takes all the energy of the collision, and it makes the people inside the car a lot safer. Well, we're not going to crash cars, but we are going to crumple something up. This concrete block. I'm going to put a target on top of this, because in a second, we're going to get a volunteer to lie on that bed of nails. We're going to put this bed of nails down on top of their chest. We're going to put the concrete block on top, and then I'm going to smash it with a sledgehammer. Okay? Now, don't worry, I've done this before, and it's hurt me. First time I did this demo, I knew that I needed goggles, because I knew if little bits of concrete came off and they hit me in the eye, it would hurt a lot. So I put goggles on. None of the concrete came towards my eyes, but a piece the size of a golf ball came and hit me in the nose. Oh, that hurt. So these days, we have more protection for our volunteer. Now, I can't get a volunteer from the audience because, as I said, this is a little dangerous. So we need a volunteer from somebody up on stage.
Peter, I have a job for you.
This is what personal assistants are for. All right, Peter, let's do this. See, but we're going to give him all the protection he needs. Because the time that I did it, you've got goggles. Do you have goggles? Good, we've all got these. Next time I did it, I decided I need a face mask. No pieces of concrete hitting me in the nose this time. They didn't. Piece hit me in the elbow. So now we have elbow protectors. Another time a little piece came off, took one of my knuckles off. It was not that bad. But we now wear gloves. So with all of that in place, I decided now is the time to get this on video. I was feeling so smug, so confident everything was going to go fine. Hired a video crew, they came in, filmed it, I'm not going to get hurt. Yes, I did. So now, we've figured it all out. This man's going to be safe because we're going to take all of the precautions we need to this time. So, let's see if we can lie you down on that bed of nails, huh? If you do this at home, do not sit down fast. Have a pillow for your head. Otherwise, what I get is little dots all over mine. Small children come up and join them together, you know. But let's get on with this, because that bed of nails is about as comfortable as a Motel 6 bed. So, bed of nails, concrete block, and if I may, a very vital piece of equipment. The piece I forgot. Oh yeah, we have a video of me crumpling like a cheap card table. All right, 3, 2, 1. And we smash the top right off it. Oh, look at that beautiful break. Cool. You okay under there, Peter? Yeah, great. All right, let's get this man back up again. Put this away. Oh, this is so much fun. I love doing this. Oh, what's next, huh? Let's see. Gotta move the bed of nails out the way. Gotta be safe. Oh, no. I know that ring. That's Leno. He's got a time machine, too. His doesn't seem to be working any better than yours. I gotta go and fix his. He's my boss, so I gotta be...
What about our time machine?
Ooh, let's have a look. You know, I think all you need is more power.
More power.
Yep. You got a 1,000,000-volt Tesla coil right there?
Yeah.
Hook it up to the time machine. That'll get it going.
All right.
But I gotta go, folks, so thank you very much. Thank you people very much.
Well, we have used this 1,000,000-volt Tesla coil in almost every one of our 201 shows over the years, but I never thought of using it to energize a time machine.
Well, let's see if we can get back to that first show and bring you back.
All right, let's try.
Hold on a sec, Jake. I gotta go grab a wrench. I'll be right back.
Excuse me, who are you?
Well, I'm Clint Sprott. Who are
You're
you?
not Clint Sprott. I'm Clint Sprott.
You can't be Clint Sprott. Obviously, the handsome devil, Clint Sprott.
Well, you are pretty handsome, but what is this thing?
Oh, this is a ham radio that I've been working on in the garage. And if you're really Clint Sprott, then maybe you can show me how to fix it.
Well, you know, that does look like something I built about 40 years ago. You know, I think if you turned the Zener diode around, the capacitor would charge just fine and it would work.
Oh, really? But how did you know? Ah, never mind.
Well, you know, I think it would do you some good if you would stay around for a little while. You might learn some physics that would be useful to you later in life.
Well, I'd love to, but I'm due at Hamfest in half an hour, so I'd best be off.
Well, it is true. When I was about that age, I used to build electronics, and I was a ham radio operator. And in fact, that's how I got interested in physics. And that's a good way for you to get interested in science, by building things and trying to understand how things work. But you know, with ham radios, we use them to talk to people around the world. So let's talk a little bit about the physics of sound. Now, one thing you're all familiar with probably is if you go out on the side of the road and when a car is going by at high speed honking its horn, you hear something like, meow. You've all heard that, right? And it happens not just with cars, but with trains or and that's something called the Doppler effect. When the source of sound is moving toward you, it's a high pitch. When it's moving away from you, it's a low pitch. And I can actually illustrate that with this little gadget right here. This is a whistle on the end of an arm that's connected to a motor. And what I'm going to do is turn it on and let the motor spin around. And the whistle will at sometimes be coming toward you, at other times away from you. And so can you hear that funny sound? That's right. That's the Doppler effect. When it's coming toward you, it's a high pitch. When it's going away from you, it's a low pitch. Now, I have another demonstration of the same thing. Here's a little styrofoam ball, and inside is a source of sound. When I turn it on, you all hear the sound? Now, what I have to do, of course, is make it move so it's coming toward you and away from you. So I'll just put it on this string, spin it around. Can you all hear the Doppler effect? But you know, there's something rather curious. I don't hear anything unusual at all. Why is that?
You're right in the middle.
I'm right in the middle. That's right. It's not moving any closer. It's not moving any farther. It's staying the same distance from me. And so I just hear a single frequency. But you hear the frequency go up and down as it goes around.
Professor Sprott, I hate to interrupt, but I've got something that'll fix that time machine.
Rachel, that looks like duct tape.
Oh, this isn't any duct tape. This is dielectric duct tape. This is gonna do it. I promise. It'll work this time. Give it another
Okay.
try.
Well, I'm a little skeptical, but
Well, I really do want to try the time machine one more time.
all right. It hasn't worked yet, but let's try again.
Stupid.
Who are you?
Who are we? Who are you?
Well, it's hardly fair. I asked first. But I am Nikola Tesla, inventor, scientist, a little bit confused right now. Where am I? Or more pertinently, when am I?
Well, we have accidentally transported you to the year 2008 in our time machine, which has malfunctioned today.
Time travel? Mm-hmm. Fortress of Tantalus. It's terribly tempting. If I could learn the science and technology that's transpired in the past 100 years and then take that knowledge back, No, this would surely have negative consequences. Oh, look who it is, Mr. Thomas Edison.
Tesla. Wait a minute. What's going on? Where are we? When are we?
Well, we have accidentally transported you to the year 2008 in our time machine.
2008. Think of all the knowledge. You must lead me to your nearest library.
Mr. Edison, think about this. If we were to take this knowledge back from the future, it would be gone without any work.
No, you think about this. If we can garner knowledge about the future's problems, then we can go into the past and solve them from our present.
Or cause more problems.
No,
I think that perhaps we should just discuss this back in the safety of our own time.
I'm not discussing anything with you.
Just come back here. So this is your time machine. Does this look like an outhouse to anyone else?
It said David Willey. He has such a sense of humor. He made this time machine look like an outhouse. But speaking of David Willey, maybe we should try to get him back out here to find out why his idea didn't work.
Well, I don't know. David Willey might be kind of busy. But I do know another person I could call that could come and fix this, so why don't I give him a call?
Why, it's Bassam Chery,
Hello, Clint.
the famous chemist who inspired this show some 25 years ago by his own presentations in chemistry.
I'm very happy to be here on this very special anniversary of yours.
I didn't know you knew anything about time machines.
Well, somehow I'm here. And you know, it's been 25 years since you started this program, and I'm very, very, very proud of what you have done and all that you do for not only our local community, but the community of youngsters and kids of all ages all over the world. So I brought you a token. This is your silver anniversary, 25 years, and this is a token of appreciation for you.
Oh, well, that's so kind of you, but this doesn't look silver at all. It looks like copper.
It is copper. It is copper, but you know, if you study science, you know how to change one element into another. So this is made of copper, and we can change it into silver.
Now, how would you do that?
Do you? I need a source of heat. Do you have a burner here?
Sure, we have a burner right
All right,
here.
let's go back there. And so I have with me a couple of items that I'm going to use here. So I have this casserole. It's empty except for air. And we're going to put it right there. And then I'm going to put my goggles on.
I have mine right here.
All right.
Absolutely.
All right, safety is paramount. And I'm going to take a powder. I'm going to put it in there. We're going to be heating it as we're doing now already. This is a granular powder. And then I'm going to take a clear and colorless liquid and put it in there. And then we're going to wait for this till it gets heated up. And actually, we can just drop this in. This is copper. And I'm going to drop it in there. Carefully. And we're going to let it cook for a while.
Okay.
So let's see now what's happening here. Do you think it's changed enough color, or wait a
I
little
think
longer?
that looks pretty silver to me.
Looks pretty silvery to you. Let's
I
see
think
it.
so.
Let's see if I can fish it out then.
Oh, yes.
I got it. So there.
Well, is that ever nice?
And let's cool it off a little bit here. So it's somewhat silvery, right? It's silvery
Well, I
enough.
think so. You know, you were so good at that. Could you make it into gold?
And gold?
Yeah, that would be great.
You're gonna make it the 50th anniversary?
I sure hope so.
Well, let's see if I can try to change this into gold now. I can't change the 25 into 50, but I'm just gonna use the heat, like so. I'm gonna heat this in the flame. Let's see what happens. Is it changing into a golden color?
Sure looks like gold to me.
And we gotta be careful how long we heat this. And then we cool it off. Ooh. We can turn the flame off now, please. And there it is. Well, it's not quite golden, but it's safe to handle right now.
Well, that's pretty amazing, and I
Well,
really appreciate your bringing that, and I will honor that.
Congratulations again, and many, many happy returns.
Thank you.
Congratulations. Thank you. That's yours.
Okay. Well, where were we? Tesla, of course, and Edison were two rivals who lived about 100 years ago, and they were very interested in electricity, among other things. So I'd like to show you a couple of demonstrations that involve electricity. And I'm going to start with the gadget over here, and I'm going to turn it on and ask you where you've seen this before. Frankenstein movies, that's right. They always have these, don't they? It's a device called a Jacob's ladder. And it consists of two metal rods that are close together at the bottom, far apart at the top, and there's about 60,000 volts that's applied between them, and it causes a spark to form at the bottom. Then the heat of the spark causes it to rise until the rods get far apart, the spark goes out, and then it restrikes at the bottom. Now, you'll never see one of these in a modern science laboratory. They're really not good for very much, other than props in old science fiction movies. But they do illustrate what very high voltages can do. Now over here we have another gadget called a Marx generator that also consists of a very high voltage. Here we have 10 devices. They're capacitors. They're like storage batteries, but unlike an ordinary battery that stores just a few volts, these capacitors store about 50,000 volts. Now what we're going to do is charge them up, and then we're going to discharge them all in series. It's like stringing 10 batteries together to make a much higher voltage. So 10 times 50 is 500,000 volts. So if Mr. Wykes will charge it up, we'll see what happens.
Okay, but I need some help from the audience, so I need a countdown. 5, 4, 3, 2, 1.
Oh. So that shows you what a spark of 500,000 volts looks like, 500,000 volts. And of course, that's what a bolt of lightning is. The clouds charge up to very high voltage, and then at some point they discharge to the earth, and you see a very big spark like that, and that's what we call lightning. Now, another gadget that makes very large voltages is this thing. This you would have seen in a laboratory maybe 100 years ago, or in a lecture demonstration. It's a plastic disc that I can rotate with a knob here, and it's charging these two capacitors up. And they go to higher and higher voltage, and at some point they discharge, and a spark occurs between those two balls. So unlike the other two devices that I showed you that are plugged into the wall and get their electricity from the ordinary power line, this gets its electricity from a rotating disc, from the energy that I'm putting in by turning this crank. And so it shows you how you can produce very large voltages with a relatively simple apparatus. Now,
Professor Sprott, are we alone? Is Tesla here?
No, it's just you and me.
Oh, good. I noticed that you lofty men of science are having some sort of a fantastical fair of physical phenomena.
Well, that's right. This is the wonders of physics.
Huh, do you mind if I stay and observe some of your...
Oh, that would be such an honor. What would you like to see?
Well, wow, this is amazing right here.
Well, yes, this is a large capacitor that we charge.
The walls are so thin. How did you do this?
Well, I didn't personally do that. They're stamped out by the thousands in a machine, and we put drinks in them, and we drink from it.
Amazing. Oh, wait, but I recognize this over here. I invented this. In fact, I think this is the phonograph that I donated to your department last week.
Well, actually, that was donated to our department by Thomas Edison, but about 90 years ago.
Huh. Do you still use these?
Well,
am I perhaps getting royalties from these?
No, well, except for Mr. Wykes. He occasionally uses these, but no, we don't use them anymore. In fact, the way we get our music now is with a device like this.
Amazing. What is it, some sort of tiny music box?
Well, it does make music, but it doesn't have any moving parts. It stores the music in electric charges.
Where is he? Where's Edison? Edison, what are you doing? Didn't we agree that we were going to go back to our own time?
You agreed to that. I don't recall agreeing to anything.
He's so stubborn. I will get you back there if I have to.
I'm not going back.
I will drive you back.
I'd like to see you try.
Okay, come on, old man.
Oh, wait. You two are acting like children. I think we have to send you both back to your time.
Okay. But before we go, you have to settle a matter of long-standing debate between Mr. Tesla and I. All these wonderful devices, these electronic devices, surely you power them off a grid of DC current.
Please explain to these people you use the much more reliable and sophisticated alternating current system.
DC,
AC.
DC,
AC.
DC.
AC.
Well, it's true that Tesla and Edison didn't like each other very much. They were rivals and they disagreed on a number of things. And this was one case where Tesla had it right because AC, in fact, is more efficient than DC for transmission of electricity, especially over long distances. But you know, I think they were both much too gentlemanly to ever have actually had a fight. So I'm not sure that was really Tesla and Edison. But they were interested not only in electricity, but also in magnetism. And I can show you a few demonstrations that involve magnetism. This apparatus over here that I was about to show Mr. Edison is another demonstration of the same phenomenon. Here we have a very large capacitor, like the ones we have there, and we're going to charge this capacitor up to about 5,000 volts, and then we're going to discharge it into this 5-turn ring of copper tubing, and then I'm going to take one of these aluminum cans, lower it down in the coil, and discharge the capacitor. And so let's see what happens. So you see it charging up, and you can see on the meter over there it coming up to about 2,000 volts, now 3,000 volts. When it gets up to 5,000 volts, I'm going to discharge it, making a very large magnetic field surrounding the can. So we're about up to 5,000 volts. Is everyone ready? Yeah. Here we go. And look what it did to the can. It in fact crushed the can. And that's because an electric current flowed around. It's an aluminum can, so it's not magnetic, but that electric current made it momentarily magnetic, and this magnet was repelled by that magnet that surrounded it, and it tried to get as far away as it could, and it crushed the can. Now, would you like to see that again? Yeah. Okay, except this time, sir, do you play baseball? You? Yeah. Okay. Take that. This time, we're going to place the can not down in the coil, but on the top of the coil. Okay, we're going to charge it up again to 5,000 volts. And ready? Here we go. Okay. Well, that shows you this principle of magnetic induction. Now, I've mentioned to you that when you cool a metal down, typically it becomes a better conductor of electricity. Aluminum becomes about a 7 times better conductor of electricity when it's at the temperature of liquid nitrogen. But there are materials that at the temperature of liquid nitrogen become a perfect conductor. And if you cause a current to flow in them, it will flow forever. And I have such a material over here. It is something called a superconductor. And it's a fairly small thing, so you'll have to look at it on the television monitor. This little black disc is a superconducting material and is sitting in a little bath of liquid nitrogen right now. Now what I'm going to do is take a little tiny magnet and some tweezers here, and I'm going to set this magnet on top of the superconductor. Now you'll see the magnet the little tiny magnet is magnetically levitated because when it tries to fall down onto the superconductor, it induces an electric current in the superconductor that repels it. And that current, unlike over here, never dies away. It keeps flowing for as long as we keep the superconductor very cold. Okay, so.
Well, Professor Sprott, you know, I'd really like to try this time machine one more time. I'd like to get you back from that first show in 1984.
Well, now, Peter, you're starting to annoy me a little bit, but all right, if you absolutely insist, let's see if it's going to work.
Okay, so
So, we're going to talk about, this is where we left off yesterday. We were talking about the radium and the polonium, and they are both very, very
Let me
active.
just
I have
visit
them here in
Zulu.
my
I'll
pocket.
be
I
right
can show
back. But this is not
you. Einstein, it's so good to see you, but I was in the middle of a lecture. Can we have a coffee or something? I mean, I think...
Okay, I'll just sit.
But these are not my students. What's going on here?
Well, who are you?
Well, I'm Marie Curie, of course. There's only one woman professor in the entire University of Paris. But who are you, and what are we doing here?
Oh, well, I'm Professor Sprott, and we have accidentally transported you to the year 2008 in our time machine.
2008? But this is amazing! Marie, it's just like I was saying. You see, time is just like any other dimension. You can go backwards, you can go forwards. This is incredible.
Yes, it's amazing, Einstein. But how does this thing work?
Well, not very well, apparently, but with you famous scientists, maybe you could fix it for us.
It must warp space-time somehow.
I don't know anything about space-time. I can tell you all about the radium. Einstein, do you know anything about this?
I'm no quantum mechanic. I'm a theorist. How can I help?
Seriously, they don't know anything. They should be in the lab like me. But, so you didn't really want us here, and we don't know how to help you.
Well, okay, maybe we should let you go back to your time. I
That would
apologize
be a very
for...
good idea. I have
You
a very
think it will
important
send us
lecture.
back?
Well, I wouldn't guarantee anything at this point, but if you step inside and pull that chain, it might work. Well, you know, Marie Curie and Albert Einstein were two very important physicists who lived about 100 years ago, and they made many discoveries that we use even today to understand the laws of physics. And one of the things that Albert Einstein especially was very interested in is light, and what happens when things move very close to the speed of light. So let me show you a few demonstrations that involve light. In order to do that, we need a source of light, and we have such a thing here. It's a very powerful laser. And it's making a beam of light that's going across, and can you see it on the wall over there? I'll shake it back and forth so you can see it. A little blue-green dot on the wall over there. And that's being produced by this laser. Now, of course, you can see the light over there, but you can't see it in here. But there is a way to make it visible to you. If I take these erasers that have some chalk dust on it and make some chalk dust in the room here, the light will scatter off the tiny particles of chalk, and you'll be able to see the laser beam. Now, the important thing to note about this laser beam is how very straight it goes. And you're accustomed to the idea that light travels in a very straight line. But you know, that's not always the case. It's possible for light to actually go around a bend. Not something you ordinarily encounter, but here I have a demonstration of that. This is a plastic rod. It's solid, and so it's transparent. Light can go through it. But it goes around about 3 loops, and then it comes out right here. I'm going to put this in the laser beam, so the laser light goes in one end of this plastic rod, and we will see if we can make it come out the other end. So can you see the light go around 3 times and it comes out over here? And this is something called a light guide. For obvious reasons, it's guiding the light around the bend.
Professor Sprott, I found a loose wire on this conductor down here, so I think I got this thing fixed, and I'd really like to try it one more time.
You know, I think you're the loose wire in this lecture, but this is absolutely the last time we're going to put up with this.
Oh,
Hello?
Excuse me, who are you?
Hi, I'm Professor Clint Sprott. Who are you?
I'm Professor Clint Sprott. You look nothing like me.
Ah, time travel, of course. So you're simply a past counterpart of myself?
No, you're a future counterpart of me, perhaps.
Ah, very true.
well, okay. So you're both Professor Sprott, but look, this is truly amazing. We've gone into the future. So tell me, old Sprott, will I live forever? Do I still have to pay taxes? Have I survived the nuclear war?
In the future, we will have flying cars,
Oh,
no government,
great.
and everybody will live on the moon.
Wow, really?
No. If I told you what was actually going to happen in the future, it would alter the future. Perhaps in a negative fashion. So I'd better be off before I cause even more disturbance to the space-time continuum than I already have.
Well, I do hope I live to a ripe old age, but you know, if 50 years from now you see me and I look like that, tell me to get a haircut. But you know, there are no time machines, and there probably never will be. And the reason is that the future is not yet determined. Any one of you could go out of here today and you could make a discovery, or you could invent something that would completely change the future. But one thing we do know is that whatever discovery you make or whatever you invent will obey the laws of physics. And that's why we've been doing these shows for 25 years, so that you will all know something about the laws of physics. And we hope when you make your discovery or invent your device that it will be something that will make a better world, not just for you and me, but for those who come after us. And just to convince you this time machine does absolutely nothing, I'm going to step inside of it and have Mr. Wykes turn it on, and you'll see it really doesn't work at all.
But I'll show you it does work. Voila! See, I told you Professor Sprott would work. Come on out. Professor Sprott, come out here. Professor Sprott! Oh no, we've lost Professor Sprott!
Oh, I'm sorry I'm late. Welcome to the wonders of physics.
Oh, wait. What do you mean, welcome to the wonders of physics? You've already done the show. We're at the end of the show now.
You mean I've done all these demonstrations?
Yes, you've done all these demonstrations. We're at the end. You need to do the end of the show.
Oh, well, okay. We'll end the show the way we have ended every one of the 201 shows we've done over these 25 years by making for you a cloud. And we do that using this container of 25 liters of liquid nitrogen. And we force nitrogen gas into it. That causes the liquid to come out through these holes on the top of this pipe. The liquid is very cold, so it will cool the air. The moisture in the air will condense into tiny droplets of liquid water. And that's what we call a cloud. And with that, I thank you all for coming.